Hi, I'm back. In this video, we'll take a look at what are enzymes and how do they catalyze reactions. So let's get to our PowerPoint. And we're here, I think. So it turns out that for spontaneous and for non-spontaneous reactions, enzymes are important in biological systems, in any reaction that happens in a living cell. Enzymes are required. And so we need to sort out what are enzymes and why are they needed for chemical reactions to proceed. All right, the first question then is, what are enzymes? Can we define them? Sure. The simplest definition of an enzyme is that most enzymes are protein catalysts. Not all enzymes are proteins, but most of them are. Protein catalysts. Oops. Okay. So what is first of all, a protein? We'll talk more about the enzyme structure in the next video, but most enzymes are proteins, complex, three-dimensional shaped molecules, right? And they're catalysts. When we say catalysts, we mean that the enzyme will speed up a chemical reaction and not be used up in the process. Catalysts speed up chemical reactions without being used up in the process. So enzymes speed up chemical reactions. And we want to know how, right? We want to sort this out. So let's think about the hydrolysis of sucrose for a minute. And then we'll think about enzymes that are an enzyme that's used to catalyze this reaction. So the hydrolysis of sucrose goes something like this. Remember that sucrose is a two-part sugar, a disaccharide. It's made up of glucose, and fructose, okay? And we're breaking it apart in this reaction into its parts. Now it says here that sucrose plus water, and we're using a hydrolysis reaction to do it, have higher free energy than glucose and fructose. So immediately I think, I'm going to draw this out in my head. I'm thinking about the free energy, that's a terrible G there, and I'm thinking about the reaction progress, and here are the reactants, here are the products. The reactants are sucrose and water, and it says they have a higher free energy, so I'm going to put it up high, the bar up high, sucrose plus water up here, than the products. The products are glucose and fructose. So there they sit. All right, so is this reaction endergonic or exergonic? Well, there's a downhill here, right? Delta G is negative. Delta G represents the change in free energy. So we take the free energy of the products minus the free energy of the reactants. So we go small minus big, we get a negative number. Delta G is negative. Oops, delta G is less than 0. Hey, guess what? This is an exergonic reaction. It's going to happen. It's spontaneous, if you will. Here's a picture, another picture of this reaction. Here we've got our sucrose molecule and water, and we're breaking it into glucose and fructose. What kind of molecule is sucrose? I think I mentioned that already. It's a disaccharide. And what is the enzyme catalyzing this reaction? So inside cells, sucrase catalyzes the reaction. Enzymes are always written above the reaction arrow. So I know that this is the enzyme. I also know it's the enzyme because it ends in the letter ASE, the letters ASE. Sucrase catalyzes this reaction. It speeds up this reaction without being used up in the process, right? Okay, but why is the enzyme sucrase necessary for this reaction to proceed at biologically relevant rate? This is a spontaneous reaction. It should run by itself, right? Why does it need an enzyme to speed it up? That's the question. Well, when we think about this is G, these are the reactants and the products. When we think about this reaction, we've got sucrose and water up here, and glucose and fructose down here. Okay? This reaction should run by itself, but any reaction, spontaneous or not spontaneous, requires a small bit of energy to activate or to get the reaction started. These molecules, sucrose and water, need to bump into each other and need to have a certain amount of energy so that the reaction can get started. So we actually would maybe draw kind of a hump here like that. This amount of energy is necessary to get the reaction started. That amount of energy is called the activation energy, or the energy of activation, E superscript A. Maybe you've seen that written like that before. Oh, sorry, subscript A. Oh, why, E sub A. There we go, that's better. I don't know how to erase little bits. Maybe I can do this. Oh no, that didn't work. Sorry, I don't know where I am anymore. Okay, we'll forget that. Okay, so it takes a little bit of energy to get this reaction started. That's the activation energy. And it turns out enzymes lower the amount of activation energy necessary to get a reaction started. That's why they can speed up chemical reactions. Here's another diagram that's drawn for us. Remember, free energy is over here. Okay. And our reactants in this case, we've got different reactants here, but we're thinking about sucrose and water. Our reactants have to react with each other. There's some energy required to kind of get them ready to react and get them in a transition state so that they're ready to undergo some chemical bond breaking and forming again, right? Rearrangement, if you will. And that's E sub A. That's the activation energy, right? There's still in this reaction a change in G, or a drop. This here represents delta G, okay? Delta G is the amount of energy that's released when this reaction finally runs, but it needs a little bit of energy to get the reaction started, okay? And it turns out that enzymes alter the course of the reaction by lowering the E sub A necessary to get the reaction started. So this black line represents the course of the reaction without the enzyme. The red line represents what happens with the enzyme. The enzyme somehow makes it easier for the reaction to get started. So think about enzymes like you might think about what happens when you're sledding. So I'm sure some of you have gone sledding if you've lived in Michigan. And when you go sledding, when I go sledding with my family, we used to always have contests. Who can make the personal record of the day would be the person who travels the farthest down the hill in one sledding bout, right? My daughter was fantastic at this, but she wasn't very good at the top of the hill. Because at the top of the hill, this is going to be a downhill reaction, literally, right? This is definitely a spontaneous reaction. You start at the top of the hill, you fall down the hill. This is going to be energy releasing. But when my daughter's at the top of the hill, you're sitting perched on the top of the hill. It takes a little bit, a little push, if you will, to get started, to get over the top of the hill and get started. Think of that as the activation energy. I often help my daughter by giving her that push. I was like the enzyme that kind of lowered the energy necessary to get the reaction started, right? That's what enzymes do. Now, I do have one question for you. Do enzymes affect the overall delta G for a reaction? Do they change the overall delta G for a reaction? Let's look at this picture again. Look at the two lines, the black and the red line. Look at delta G. Does delta G change with the black or the red line? No. Delta G is still the same, okay? There's still a certain amount of energy released as this reaction happens. That's delta G from the reactants to the products. The only thing that changes is the change in E sub A, right? Delta G doesn't change at all. So we're going to say no. Oops, scratch that out and write it a little more neatly. No. Okay? Perfect. So we're going to take a look at, in the next video, at the enzyme structure and how it relates to its function. Like, why is it that enzymes lower E sub A for reactions? So we'll take a look at that next time. Okay.